Welcome to Ask and Learn.
A sample of food is burned in a bomb calorimeter, and the water temperature rises by 3.2 degrees Celsius when equilibrium is established. We wish to calculate the energy content of the food. So we assume that water is an incompressible substance with constant specific heats. Air is an ideal gas. The energy stored in the reaction chamber is negligible, and the energy supplied by the mixer is negligible. So the specific heat of water at room temperature, C, is equal to 4.18 kilojoule per kg degrees Celsius, and the constant volume specific heat of air at room temperature is 0.718 kilojoule per kg degrees Celsius. Now these values we get from our tables. So the chemical energy released here during the combustion of the sample is transferred to the water as heat. So if we disregard the change in the sensible energy of the reaction chamber, the energy content of the food is simply the heat transferred to the water. So since our system is a closed system, we can write an energy balance relation, E in minus E out, is equal to the change in energy of our system, delta E. So this becomes, now the only energy in is due to heat in the calorimeter. So that's Q in, and this is responsible to the change in internal energy of the water in the calorimeter. So the heat is transferred to the water and causes a change in internal energy. And we can relate this internal energy to the change in temperatures by the mass of water times its specific heat times the change in temperature, T2 minus T1. And so we can essentially find the energy content of the food. Now, these values are all known, so we can find this value for Q. So that's 3 kg multiplied by C for water is 4.18, and that's kilojoule per kg degrees Celsius, times a temperature change of 3.2 degrees Celsius. And so we get the heat energy into the system for the 2-gram sample to be 40.13 kilojoules. But remember, that's for a 2-gram sample. So the energy content of the food per unit mass we'll calculate as follows. This is 40.13 kilojoules for every 2 grams of mass of the food, and we'll convert the grams into kilograms. So 1,000 grams make a kilogram, and hence we get the energy content of the food per unit mass to be 20,060 kilojoules per kg. So that's the energy content in the food per unit mass. Now, we wish to calculate, to make a rough estimate of the error involved by neglecting the thermal energy stored in the reaction chamber. So we'll treat the entire mass within the chamber as air and determine the change in the sensible internal energy. So delta U within the chamber, the change in internal energy of the chamber, is equal to mc times delta T, the change in temperature in the chamber, which we assume is only air. And so this is 0.102 kgs times the specific heat of air, 0.718 kilojoule per kg degrees Celsius, and a temperature change of 3.2 degrees Celsius. And so we get the internal energy change of the chamber to be 0.23 kilojoules. So if we look at this energy compared to our energy into the system, or the energy that the water gets from the combustion, this is less than 1% of the internal energy change of the water. And so therefore it is reasonable to disregard the change in sensible energy content of the reaction chamber in this analysis.